Slide 1. Electrophysiology of the Heart is a series of slide tape programs developed and produced by the American Physiological Society. This is Electrocardiography, Fundamental Theory, Part 2. Content expert, Dr. Morton F. Arnsdorf. 2. Your understanding of the theory presented in Electrocardiography, Fundamental Theory, Part 1 is prerequisite to successful completion of this program. Part 1 presented the distributed dipole model and solid angle analysis of the relationship between the electrical activity of the heart and potential differences detected and recorded electrocardiographically. This theoretical approach provides physiological interpretation of the electrocardiogram, since it recognizes the spatial and non-spatial factors that influence the magnitude and polarity of the electrocardiogram. The difficulty of mathematical description and calculation, however, limit the practicality of solid angle analysis. Primarily for this reason, simplified theory is commonly used. 3. The single equivalent dipole model and equivalent vector concept provide a simplified theoretical approach to the description of cardiac electrical activity. The assumptions and theoretical framework necessary for application of this model to electrocardiography are the subjects of this presentation. 4. Questions and answers are provided throughout this program to allow you to assess your readiness for the program, your progress during development of the concepts, and finally, your overall comprehension of the material presented. After a question is stated, you must stop the tape while you formulate your answer. Many of these answers require you to make rough sketches or simple drawings. After an answer is explained, you must stop the tape to assess your response. Of course, you should also stop the tape whenever you want to study the visual material. The prerequisite test begins on the next slide. 5. Make a sketch of this dipole and add several current flow lines and isopotential field lines. Indicate the polarity of potentials detected at points P1, P2, and P3. 6. Your drawing should show current flow lines and isopotential field lines similar to these. The potential detected at P1 is positive, at P2 negative, and at P3 zero potential is detected, since it is in the plane of zero potential perpendicular to the center of the dipole axis. 7. Complete this definition in terms of the distributed dipole model. 8. A difference in transmembrane voltage between two regions of the myocardium creates a boundary. Theoretically, the boundary is represented by an infinite number of dipoles. 9. In this stylized view of the ventricles, one area is depolarized due to injury. This creates a stationary boundary. What is the geometric measure of the boundary, viewed from point P, called? And what are its determinants? 10. The geometric measure of the boundary is the solid angle, omega. It is the area on the surface of a unit sphere at point P subtended by a cone of radii drawn from each point on the boundary to the measuring point. The determinants of the solid angle are the size of the boundary and the distance between the boundary and the recording site P. 11. This equation represents the factors that determine the magnitude of the potential generated by the heart and measured at a given point. State whether each factor is spatial or non-spatial. 12. The solid angle, omega, represents the spatial determinants of the recorded voltage. 13. In this program, we will discuss the distributed dipole as represented by multiple and equivalent vectors, translation, summation, and projection of vectors, cardiac electrical activity as described by an equivalent spatial vector, 3 electrocardiographic lead systems used in the analysis of cardiac electrical activity, and the assumptions necessary to consider the heart a true dipole current source, and some limitations of the theory. This is not a course in clinical electrocardiography, but rather an introduction to concepts useful in the interpretation of the electrocardiogram. 14. Your first objective is to be able to describe a distributed dipole layer by multiple spatial vectors and an equivalent vector, and to translate, summate, and project vectors spatially and on a plane. 15. Dipoles have magnitude and are directed in space along their axes. Dipoles, therefore, can be represented by vectors, and dipoles with specific spatial orientation can be represented by spatial vectors. By convention, the arrowhead of a vector represents the positive pole of a dipole, and the length of a vector represents the magnitude of a dipole. 16. Vectors may be summed according to rules that permit the net effect of multiple spatial vectors to be expressed in terms of a single equivalent spatial vector. 17. In the development of a simplified model for the electrical activity of the heart, the distributed dipoles of each boundary developed during cardiac activation may be represented by an equivalent spatial vector. 18. Spatial vectors may be translated. That is, they may be moved in space without changing either their magnitude or direction. 19. Spatial vectors, once translated to a common origin, are referred to as component vectors and may be summed by the parallelogram method. A parallelogram is constructed to the component spatial vectors, and a resultant equivalent vector is drawn diagonally from the common origin of the component vectors to the opposite angle. 20. In the classical single dipole model, the heart is viewed as a single dipole current source and is represented by a single equivalent spatial vector, which varies in spatial orientation and magnitude during cardiac activation. 21. To analyze a resultant equivalent spatial vector, it may be projected onto a plane. Perpendicular lines are constructed from the plane to the origin and terminus of the spatial vector. This establishes the magnitude and direction of the projected vector in the plane. 22. A vector projected onto a plane may itself be projected onto any axis within the plane. In this example, the origin of the vector is at the intersection of two axes at right angles to each other. A line constructed from the terminus of the vector perpendicular to the axis establishes the component of the vector in the chosen axis. 23. Conversely, given component vectors within a plane, a resultant vector may be constructed. Planes, axes, and the electrocardiographic lead systems by which they are defined will be discussed in the following section. 24. This represents a cardiac activation wavefront and its associated multiple spatial dipoles. Sketch the multiple spatial vectors and single equivalent vector that describe the electrical behavior of the boundary. 25. Each dipole of the boundary can be represented by a spatial vector, and the vectors can be summed and represented by a single equivalent vector. 26. Sketch these pairs of component vectors and construct the resultant vector for each pair. Which resultant vector has the greater magnitude? 27. Component spatial vectors are summed by the parallelogram method. The resultant equivalent spatial vector on the right has the greater magnitude. An equivalent spatial vector is projected onto a plane. Construct the components of the projected vector on each axis. 29. By constructing a perpendicular line from the axis to the terminus and origin of the resultant vector, you establish the polarity and relative magnitude of the component vector in each axis. 30. Your second objective is to be able to represent the electrical activity of the heart by a single equivalent spatial vector projected onto the planes and lead axes established by 3 electrocardiographic lead systems. 31. Electrodes on the skin and their electrical connections to a galvanometer or electrocardiographic recorder constitute leads. Each lead records the same series of electrical events occurring in the heart, but views the events from a different electrical perspective. 32. 2 types of electrical connections will be discussed. A unipolar lead compares the potential detected by a positive exploring electrode with a negative electrode established at an electrically indifferent, or so-called zero, potential. A bipolar lead compares voltage variations at 2 points and registers the difference between them. 33. Note the polarity designations for electrodes and electrode connections. A line between the electrode locations, or their electrical equivalents in the body, is the electrical axis of a lead. A galvanometer or electrocardiograph responds to electrical forces parallel to its electrical axis. Therefore, in order to characterize the direction of an electrical force detected in a lead axis, polarity for the system must be established. 34. We will first consider the bipolar leads suggested by Einthoven. Lead 1 connects the left arm with the right arm. The left arm is positive with respect to the right arm. Lead 2 connects the right arm with the left leg, and lead 3 connects the left arm with the left leg. The left leg is positive with respect to both arms. 35. In the Einthoven system, the limbs are considered to be electrical conductors representative of the potentials established by the heart at each shoulder and at the pubic symphysis. Lines connecting these points are the electrical axes of the Einthoven system. 36. The Einthoven lead axes are considered to be equidistant from the heart. Therefore, a cardiac vector in the plane of the axes with its origin at the central 0 point may be projected onto each lead axis. Each component vector represents the polarity and magnitude of the electrical force detected in that axis. 37. Since the Einthoven axes are considered equidistant from the heart, the 0 point of each axis may be translated to a common central 0 point. Again, a cardiac vector with its origin at the 0 point may be projected onto each lead axis. 38. The Einthoven lead system defines the frontal plane with a left-right and superior-inferior orientation. 39. In this example, the component of the cardiac vector detected in lead 1 is large and directed toward the positive pole of the axis. This results in a large upward deflection in the lead 1 ECG recording. The component in lead 3 is smaller and is directed toward the negative pole of the axis, resulting in a downward deflection in the lead 3 ECG. 40. Given the Einthoven lead axes and a cardiac vector in the frontal plane, make a sketch and label the lead axes and their polarity. Project the vector onto the leads, state the polarity of the voltage recorded in each lead, and state which vector produces the largest voltage recording. (41) The projected vectors indicate positive deflections in leads 2 and 3, and a negative deflection in lead 1. The largest deflection is in lead 3. (42) Given the relative magnitude and polarity of component vectors in leads 1 and 3, construct the resultant vector and estimate the relative magnitude and polarity of the ECG recording expected in lead 2. (43) The resultant vector is established by constructing perpendiculars from the component vectors. The projection of the resultant vector onto lead 2 indicates a small positive deflection. (44) The augmented unipolar limb leads of Goldberger provide a second conventional lead system that defines the electrical activity of the heart in the frontal plane. In this example, the electrode locations for lead AVR compare the potential in the right arm with an indifferent or zero potential created between the left arm and left foot. 45. The electrical axis of lead AVR on the thorax is on the line from the right shoulder to the indifferent point created between the left shoulder and the pubic symphysis. The right shoulder is positive with respect to the indifferent point. 46. Lead axis AVL compares the potential at the left shoulder with the zero point between the right shoulder and the pubic symphysis, and AVF compares the difference between the potential at the pubis and the zero point between the shoulders. 47. Applying the principles developed thus far, a cardiac vector at the zero point of the Goldberger axes may be projected onto the axes and ECG recordings estimated. In this example, you would expect a moderate positive deflection in AVL and a large negative deflection in lead AVF. 48. By combining the electrical axes of the bipolar leads of Einthoven and the augmented unipolar leads of Goldberger, we define the hexaxial reference system for the frontal plane. Study the designations of these axes and their polarity. 49. Conventionally, the direction of a vector projected onto the frontal plane is described by its angle from the horizon, with the positive pole of lead 1 considered 0. Upward angles are negative and downward angles positive. 50. In this example, assuming that each division on the scale is equal to 1/10 millivolt, a positive deflection of 2/10 millivolt on lead 1 and a positive deflection of 9/10 millivolt on lead AVF will result in a vector whose magnitude is about 9/10 millivolt projected at plus 85 degrees. Again, the angle of the projected vector reflects the position of the cardiac vector in the frontal plane. 51. Each division of this hexaxial system represents 1/10 millivolt. Given the component vectors in leads 1 and AVF, construct the resultant cardiac vector and project it onto leads 2 and AVR. Sketch the polarity and approximate the magnitude of the ECG deflections you would expect in these leads. (52) The resultant vector lies at about plus 45 degrees and results in a positive lead 2 deflection of approximately 55 hundredths millivolt and a negative AVR deflection of approximately 55 hundredths millivolt. 53. The system of unipolar precordial chest leads, suggested by Wilson, views the cardiac dipole from a different perspective. In this system, the three standard limb leads comprise a central terminal at an indifferent or zero potential against which the positive exploring electrode compares potentials at various positions on the thorax. 54. The exploring electrode in the Wilson system is placed in the following locations. V1 and V2 are in the fourth intercostal space, somewhat to the right and left of the sternum, respectively. V3 is placed between V2 and V4, with V4 positioned in the fifth intercostal space at the midclavicular line, and V5 and V6 are placed at the same level as V4 in the anterior axillary and mid-axillary lines, respectively. 55. The anatomic positioning of the unipolar chest leads essentially defines the horizontal or transverse plane, with a left-right and anterior-posterior orientation. 56. The three bipolar leads of Einthoven, the three augmented unipolar leads of Goldberger, and the 6 unipolar leads of Wilson comprise the 12 conventional leads of the ECG. They provide 12 electrode locations from which the same electrical events occurring in the heart can be viewed. 57. Given this diagram of the precordial chest leads of Wilson and the orientation of a spatial cardiac vector on the plane, sketch the projection of the vector on leads V2 and V6 and approximate the magnitude and polarity of ECG recordings in those leads. '58. You would expect a large positive deflection in V2 and a small negative deflection in V6. 59. Your third objective is to be able to describe the assumptions necessary to consider the heart a true single dipole current source, and to state the limitations of this model. 60. In our discussion of the single equivalent dipole model, we have made a number of assumptions which, although useful, are at best a rough approximation of the actual situation. For a single dipole to be a true approximation of cardiac electrical activity, the volume conducting medium of the thorax would have to be homogeneous and infinite. The thorax is neither homogeneous nor infinite. Non-uniformity and alterations of conductivity between the heart and the recording electrodes may affect the magnitude and polarity of the potentials detected. The following structures and interfaces between these structures may influence the recorded voltage: intracavitary and intravascular blood, the heart and great vessels, the pericardium, lungs, rib cage, muscle, fat, mediastinal structures, skin, electrode paste, and the location and geometry of electrode placement. 61. It must also be assumed that the Einthoven and other lead axes are equidistant from the heart, permitting their translation to a central point, and it must be assumed that the origins of cardiac spatial vectors may be translated to the same zero point. Actually, when the inhomogeneities of the thorax are considered, the standard limb lead axes do not form an equilateral triangle, and the zero point is eccentric. 62. Finally, for the single dipole model to be a reasonable approximation of cardiac electrical activity, the lead axe's distance from the cardiac dipole must be large in relation to the size of the heart. Only at distances beyond 5 times the radius of the heart are electrical potentials recorded similar to those which would be generated by a single dipole. This requirement is not met by precordial recording sites. 63. In Electrocardiography Fundamental Theory Part 1, we discussed solid angle theory predictions of relative QRS deflection polarity for precordial, intracavitary, and epicardial recording sites as a function of myocardial infarct size. The theoretical curves described the experimental observations quite well. 64. The conceptual simplification of single equivalent vector analysis reduces the extent of physiological interpretation available in solid angle analysis, and could not have predicted such quantitative QRS changes. Nevertheless, the vectorial approach to electrocardiographic analysis is conceptually useful and necessary for understanding the basic concepts used in interpretation of the electrocardiogram. 65. Briefly state 3 assumptions which must be made in order to consider the heart a true dipole current source that may be represented by a single equivalent vector. Give a limitation for each assumption. 66. For the heart to be considered a true dipole current source, 1. The volume conductor should be homogeneous and infinite. The thorax is inhomogeneous and finite. 2. Einthoven and other lead axes should be equidistant from the heart. Considering the inhomogeneities, they are not. 3. Any lead axis should be a distance of 5 radii of the heart away from the heart. Precordial leads are not. 67. We have discussed a simplified theoretical approach to cardiac electrical activity, in which the heart is considered a single dipole current source and is represented by a single equivalent spatial vector. Also, we have developed basic concepts necessary for application of this model to electrocardiography. The post-test begins on the next slide. 68. Given 2 spatial vectors with their origins at the 0 points of 2 lead axes, sketch the projection of each vector onto its lead axis and state its magnitude and polarity. Each division on the axes equals 1/10 millivolt. 69. The point to be remembered is that the voltage recording reflects the relative polarity and magnitude of electrical forces parallel to the lead axis. In this case, the ECG records identical 2/10 millivolt positive potentials. 70. Given the unmarked axes of the hexaxial reference system, label and indicate the polarity of each axis, and name the 2 lead systems which establish the axes. What plane does the hexaxial reference system define? Indicate 0 degrees, plus 90 degrees, and minus 90 degrees. 71. The bipolar lead system of Einthoven establishes leads 1, 2, and 3. The augmented unipolar limb leads of Goldberger establish leads AVL, AVR, and AVF. The hexaxial reference system describes the frontal plane. 72. Given component vectors in leads 1 and AVF, construct the resultant vector. Project the resultant vector onto leads 2 and AVR and sketch the recording expected in each lead. Each division equals 1/10 millivolt. 73. The resultant vector falls on the lead 2 axis and results in a positive deflection of approximately 6/10 millivolt. The projection of this vector onto AVR indicates a negative deflection of approximately 55/100 millivolt. 74. Given the diagram of the precordial chest leads and the orientation of a spatial vector in the plane, sketch the projection of the spatial vector in leads V1 and V6 and sketch the voltage recordings in these leads. '75. The V1 deflection is negative. The V6 deflection is positive. The component vectors are approximately equal in magnitude. '76. The next question deals with this equivalent spatial cardiac vector projected onto both planes. '77. The projected spatial vector has this appearance in the planes. Roughly sketch the component vectors in lead axes 1 and V6 and sketch the deflections in these leads. '78. Notice that since both lead 1 and lead V6 reflect electrical activity in the left-right perspective, and since their positive poles are to the left, they are referred to as leftward leads and would be expected to exhibit similar ECG deflections. '79. This completes Part 2 of Electrocardiography Fundamental Theory. The concepts presented in fundamental theory are applied to basic electrocardiographic interpretation in the next programs of this series, Electrocardiography Applied Theory, Parts 1 and 2. References for additional study are provided at the end of the series. This program was produced by the Education Office of the American Physiological Society.